So I want to talk about the central limits theorem. If you've watched any of my videos, you may understand my style. I am a stats professor. I'm an epidemiology professor at LaSalle University in Philadelphia. When I was younger, I was a stats major as an undergrad before I had to leave college. Unfortunately, finances made it impossible for me to finish. I was at George Washington University. I went back to school later, a couple years later, at San Diego State, majored in psychology, and then later on I started getting back into statistics. When I was at George Washington, I also interned at Western Union, and I was offered the opportunity to finish my my undergrad, and they would pay for it if I worked for Western Union for my stats degree. That was awesome. What an opportunity. Except for the person I worked for was horrible, and I couldn't stand her. I can't believe I actually gave up the opportunity to do that because I hated the person so much. Hope she's doing well though in life right now. I ended up getting into psychology, and then it wasn't until later when I discovered that there was really good stuff to do in stats that I started again. When I was getting my doctorate at the University of Maryland, I fell in love with stats again, especially structural equation modeling and then multivariate stuff. Learned from a lot of people, kept on studying, studied a little bit under Benck-Mutane with structural equation modeling because he offers so many awesome courses, and I took a lot of courses with him, and it was great, and since then, since I teach stats now, and I also have my own intro stats textbook, I felt it important to go back and prove different theories. So I'm in a noisy area, trucks everywhere, motorcycles. Isn't it awesome? It's summer, it's beautiful, and people like to drive where I live. So I figured out, I'm never satisfied knowing what I know. There's always a deeper level of knowledge that one has to attain, and as a professor, I get these really bright students who sometimes ask me for more. Yeah, they ask the yeah but questions, and I love being able to answer them, and I hate when I can't answer them. So I went backwards in time. Like I had my own DeLorean time machine, went back in time and started doing mathematical statistics again. So that's just like when I was an undergrad, we had to take mathematical stats. But you're talking about, so I was an undergrad in 1984, when I was an undergrad in stats, and it's like 2000, and what is it, 2021 now? So it's been a long time since I did that. So I started relearning all the stuff I had to do. And what I focus primarily on is some of the more fundamental theorems that we deal with, or distributions, I should say, improving them. Like I did the binomial. I have video on the binomial, the Bernoulli, the Poisson. You can see these under my site. The normal, proving the normal distribution is indeed a probability density function. But I started thinking how important the normal distribution is, and it kind of like in my view, and in probably most statisticians' views, it's the most important distribution there is in statistics. We could argue for some of the other ones, because we do use the binomial a lot, and we use the Poisson. But the normal distribution is the distribution. When we talk about parametric statistics, we're really talking about statistics involving a normal distribution. Why? Well, the normal distribution is the distribution we know the most about. I mean, I could take that distribution and I can calculate a person's percentile rank in relation to others in the population. I can do so much. Like, for instance, we know with a standard normal distribution, the mean of 0 and a standard deviation of 1, that there's this rule called the 68, 95, 99.7 rule. I mean, 68% of all population values are between plus or minus 1 standard deviation of the mean. 95% are between plus or minus 2 standard deviations of the mean. 99.7% are within plus or minus 3 standard deviations of the mean. Very useful knowledge when you take that together with knowing that 50% of the distribution is below the mean and 50% is above. I could do something like say, well, if you score 1 standard deviation above the mean on whatever test, you're above 50% plus half of the 68 is 34. You scored above 84% of all others taking that same test. So that's why we love this distribution. We also can use the z-test, which is a test when we know the population mean and population standard deviation. We can compare a sample to it. We can use a t-test when we have smaller samples or when we don't know the population standard deviation. But then when the population gets large enough, and that's where we are today, our sample size gets large enough, we can the t converges to the standard normal distribution. So that's what we're talking about today, is the central limits theorem. So the central limits theorem is all about this convergence in distribution. So I went back and studied it. I studied it a lot. I used a lot of different sources, both scholarly and then also educational videos from certain professors that I like. My favorite is this professor. I wish I could remember his name right now. Embarrassed by it, from Harvard, who has his stats course. He's awesome. And a whole bunch of other articles that I read from different universities, different articles, journal articles I read using Google Scholar. I actually prefer Google Scholar for finding peer-reviewed articles, and you can actually look up my Daniel Rodriguez, my Google Scholar page if you want to see the stuff that I've done. But there's so many different ways to prove the central limits theorem, but you need a lot of knowledge to do this thing. First of all, you need to understand what a sampling distribution of the mean is. So if we took a whole bunch of samples of size n, whatever n could be, like 20 or something like that, we took every possible sample of that size, took the mean of each of those samples and plotted those means, we'd get the sampling distribution, the mean. The mean of all those sampling means is the population mean, and the standard deviation of those sampling means is what we call the standard error of the mean. I actually have, I should have brought this up. I have the calculation that shows that what I just said, the proofs. So this isn't really about this. This is more of a central limits theorem, but since you kind of need to know this, so the expected value, so that's the expected value is like the mean of the sampling distribution of mean is mu, as I mentioned, but you have to prove that, and you can do this with this really elegant and very simple proof. I love it. You know, essentially we take the expected value of the mean, right, which is the sum of all the x values divided by n. And what we know about expectations and sums, like the expected value of the sum is the sum of the expected values. The expected value of x sub I, in this case, that's one of our random variables, is itself mu, and then it just works through canceling out, because sum of mu is the same as adding mu n times, so it's n times mu. Isn't that elegant and beautiful? It just equals mu. We can do the same calculating the variance. It's actually really quite simple, and this assumes independence because we don't have to deal with covariance when they're independent. So the variance of the mean is the variance again, which we have the same. This is the same as this, right? This is just another definition of the mean. It's sometimes you'll see this as n to the negative 1 because that's 1 divided by n. When we pull it out of the variance, though, it's squared because the variance is a square term, right? It's actually the square of x sub I minus the mu, the sum of that, right? So it's a square term. So you pull it out, it's n squared, and then we're basically the same as we were before, except for now we have the variance of the sum of the x sub i's, which is the same as the sum of the variances given that they were independent, right? That's why we can do this, and we know that these variables in this case are independent. And what's important for the central limits theorem is they're identically distributed. We call that IID for independent and identically distributed. So we get the summation of sigma squared because the variance of x is sigma squared, and again we have n times sigma squared because this is a constant, so it's just n times that, and it works out to be sigma squared over n. Sometimes you'll see the standard error as sigma divided by square root of n. So that's just the square root of this variance. Elegant, beautiful, I love it. So here now we're dealing with the central limit theorem. This just states that as the sample size increases, right, as the sample size increases, this summation of all of these random variables, these IID, independent and identically distributed random variables, when standardized, so they're standardized here, right? Standardization just means you subtract the mean and you divide by the standard deviation. So if you've ever wanted to see where you stand in relation to the population on some kind of standard population, what you do is you take your score, subtract the mean from it, and divide by the standard deviation. That's how you get your z-score, right? So this is like a bunch of z-scores here. Well, the central limit theorem says that as n approaches infinity, that means as the sample size grows and grows and grows to infinity, these standardized variables, or the distribution of these standardized variables, approaches the standard normal distribution. We know the standard normal distribution for having a mean of 0 and a standard deviation of 1. So this symbol here with the little arrow with a D on it is just converges in distribution. And we talk about the normal distribution, n, with a mean of 0 and a standard deviation of 1. So it's just a notation we use. However, we can also discuss this in terms of this sampling distribution of the mean. And what I show here at equation 2 is the equation for the sampling distribution of the mean, which should look familiar. So it's the mean minus, so this is the sample mean minus the population mean, divided by the standard error of the mean. So it's the same thing as up here, except for now we're dealing with individual values. The reason we have n times mu is because we're summing these individual values. For each individual random variable, you subtract the mean from it, but you're doing that n different times because the mean is a constant. And the sigma, or the standard deviation, we're doing the variance. We're doing the variance n times, and taking the square root of the variance is the square root of n times sigma, instead of sigma squared. So that's why you have this here. But I just show you how you can derive one from the other here. So this is, if you're interested in dealing with the sampling distribution of the mean, you can easily convert this elegantly to what we're dealing with in equation 1. And again, they approach a convergent distribution to the standard normal distribution. All right, let's do this. I've seen so many different ways of approaching this issue. I mean, you don't have to assume that mu is 0 and sigma is 1. Now that you can. I mean, as long as you make explicit your assumptions, everything is fine. If I do this, so here's our equation. If I assume that mean is 0, so this n times 0 will be 0, so I get rid of that term. And sigma is 1, I get rid of the sigma, right? So that's how I come up with this term, this equation here. If I let s sub n, so the sum of the n different values, equal sigma xi, so that's this term up here, right? The numerator. So we're just simplifying for whatever reason. It makes it a little bit easier to simplify. I mean, I don't have to write this dang sigma everywhere with I equals 1 to n, you know, the summation. It's okay, so same thing here, right? That's all it's saying is that this distribution converges to the standard normal distribution as n approaches infinity. Now, here's something that we know. First of all, we have moment-generating functions. Moment-generating functions generate moments. The first moment is the mean, and the second moment is used to calculate the standard deviation. And these are two important characteristics of a distribution. In fact, they define the distribution. So we need to, if we can show that all of our random variables, all of our xi random variables are independent and identically distributed. Because they're identically distributed, they have the same moment-generating functions with the same mean and the same standard deviation. If we can show that those MGFs, or the MGF for that random variable, approaches the MGF for this variable x, whatever it is, or in this case actually it's variable z. So I use z because I talked about standardization. So I use capital Z here to indicate this standard normal population with this beautiful distribution. So I want to show that the standardized random variables, the x sub i's, converge to this moment generating function that's associated with the standard normal distribution. And in a different video somewhere, and you can find it in one of my videos, so all of my stats videos are linked together, I prove this moment generating function for the normal distribution. And this is for a standard normal distribution. It's 2 squared over 2. So really what we want to do is we need to prove that as n approaches infinity, this moment generating function for these independent and identically distributed random variables, the x sub i's, approach e to the t squared over 2. That's what we need to do. Okay, so that's our goal here. Let's do it by first finding the MGF for our random variables. So this is fun. All right, so our random variable is s of n divided by square root of n. Right, so the moment generating function for that is, well, a moment generating function is basically an expectation. So it's the expected value of e to the power. So e, if you're not familiar with, it's Euler's number. It's 2.7 something. I can't ever remember it, and it's almost irrelevant that I'm not Rain Man, so I don't have to remember it. So it's e, the expected value of e to the t times this, the expected value of e to the t times the random variable itself. And in this case, it's s of n divided by the square root of n. If we recall, s of n is the summation of all the xi's so s stands for summation of all the n x sub i's. So knowing a little bit about algebra, knowing something about exponents, we can ascertain what we need here. So we have the expected value of t times the summation. So now I'm expanding this s sub n. So summation from 1 to n of the x sub I. Beautiful, huh? So I can actually expand this to being what? As a summation. So it's t over square root of n times x1 plus x2 plus x3 all the way to xn. As you know, I hope you know, this sum can be rewritten as a product of the different exponential functions, right? So this could be e to the t square root of n x1 times e to the t over square root of n x2, and so on going n times. So I use this product. I love these little this pi for product here. This product. So I'm multiplying this n different times. So that's all that's saying, and I'm taking its expectation. Now, here's the fun part. Because we know our random variables are independent, then the expected value of the product is the product of the expected values. But it's because it's independent, they're independent, right? So now we're actually, this is a moment generating function right here, right? This is a the expected value of e to the t xi over n. That's a moment generating function, and we're doing it n different times, so we can just raise this MGF, and that's what I do here, this MGF to the nth power, and that's where we are. Beautiful. Okay, so what do we do now? Well, this is again assuming that n approaches, we're dealing with n approaching infinity, and that is problematic though, because as n approaches infinity, this value here approaches 0, right? Okay, so this denominator is getting really, really large relative to the numerator, so this is going to become 0, and m of 0, so that's going to be e to the raised to the power t over square root of n times times x. Well, that's going to be 0, right? E to the 0 is 1, so we're going to get 1 to infinity, which is an indeterminate form. Now, it's interesting because you can go and discuss this with many mathematicians. Some will say, no, actually, it's not an indeterminate form. But we treat it as an indeterminate form because there's many different ways we can arrive at 1 to infinity. So we're not really sure what this this value is here. So that's an indeterminate form. So that leads us to think about L'Hopital's rule, but I need this in the form of a quotient. So if I take the log of this value, I get n log of this moment generating function. And to make this into a quotient, I divide the numerator and the denominator by n. So this is where I get. Now it's beautiful. All of a sudden, okay, now we're talking. We're going to get 0. We're going to get 0. Log of 1 is log of 1 is 0, right? So we're going to get 0 over 0. So we are kind of where I want to be right now, sort of. So, but I can simplify this if I let y. So I do a variable transformation, variable substitution. So if I let y equals 1 over the square root of n, so now I rewrite this, and why this is good is because my denominator now is y squared. So since I let y equals 1 over square root of n, as n approaches infinity, this y approaches 0, so I can rewrite my limit as y approach, the limit of this as y approaches 0. But now, taking L'Hopital's rule, I take the derivative of the numerator and the denominator. The derivative of the denominator with respect to y is 2y. So it's 2 times y, so 2 minus 1 is 1, so that's why I got 2y. So you just got to know your derivatives. And for this one, okay, so the derivative of the log of mty is 1 over mty times the derivative of this function here, okay, which is t, right? So this is with respect to y, so it's t, first derivative of the moment generating function, divided by 2y over mty. That's what we got from doing that derivative. So now I have to take the second derivative of this moment generating function in the numerator, because this is still indeterminate here, because you still have this y here, and we know y is approaching 0, so we're kind of still in the same boat, right? And we know that the first derivative of 0 is going to be 0, because we know first derivative of the moment generating function at 0 is the mean, so we got 0 over 0 again, so that's a problem. But we can pull out this 2t, this t over 2. Okay, so now we have to take the derivative again. Right, so we're going to do that again, right? So this is just rewriting what we have up here, okay? So we take the second derivative, and here now, this is like a chain rule issue, right? So we got a derivative of the outside times the derivative of the inside. So the derivative of the inside with respect to y is t, so we get the second derivative, right, of the outside, and the derivative of the denominator, since it's just y times, so y times mty. So as y approaches 0, this is m of 0, so that's the same as e to the ty, and y is 0, so that's e to the 0. So this is going to be 1. So we end up having 1 in the denominator, and the derivative of y is just 1, right? Because with respect to y, it's just 1. So we have this nice limit. We have this t that we pulled out here when we differentiated this mgf again. All right, so this is where we're at right now. So where are we? So we got t over 2, t, we got the second derivative of the moment generating function, ty. Okay, so what is the second derivative? The second derivative, I mentioned before, is used to calculate the variance. Well, generally, it's the second derivative from the moment generating function minus the first derivative of the moment generating function at 0, which is the mean squared, right? Well, we know the mean squared is 0 because we said the mean was 0, right? We said it was 0 and the variance was 1. The second derivative is the variance in that case, so that's just 1. So we have t times 1 here over 1. And this is actually a constant because we're actually, the limit is as y approaches 0. I don't see any y's here, so this is a constant, so we can get rid of this limit. The limit's going to be t over 1. So it's going to be t times t is t squared over 2. Almost done now, right? We're almost done. So we took the log in order to use L'Hopital's rule. So what we have to do here is exponentiate. And we get e to the t squared over 2, which is exactly what we were looking for. So we've shown in this beautiful and very elegant proof that as n approaches infinity, the distribution of these IID random variables, regardless of what they are, they could be, I just said they're IID, they could be Bernoulli, they could be binomial, whatever, approaches the moment generating function of the standard normal distribution. And because of that, we can say that the distribution of these random variables when n approaches infinity converges to the standard normal distribution. That's that proof. Now that's one way to do the proof. There is another way to do the proof. I'm not going to do it now. I may do it later. It's a little bit more complicated. It's using the Taylor series. I actually like that one a lot, but you really need to know about what happens to the Taylor series as it moves on to infinity. You can use this big O. I've seen it done with the big O notation. I've also seen it done with the she variable. Very creative, right? But it's just another way of doing. This is actually a simpler way of proving it. I find it simpler, but you can also do it the other way. So there's at least 2 different ways that you can approach this. There's also characteristic functions, but I'm not going over there. You know, I'm interested in statistics, and this is what my goal is, to show you that the proof of the central limit theorem. Thank you very much, and I hope you enjoyed this. Comment if you'd like.